Hello, everyone. It is a couple minutes after 2 o'clock, and what we are going to do today is continue on with confidence intervals and maybe do a problem or two. And I'm going to introduce you to the t-table and the t-distribution. Okay, so what we've had so far, and I had written 3 formulas on the board that all look very, very, very similar, right? And I'm going to put them on the board again. And these are how you do confidence intervals, right? And the ones we're going to do today are the basic ones. And then on Monday, I'm going to introduce what is a chapter 8, which is confidence intervals using proportions or percentages, right? And those are a little bit different. That formula looks different. And we're going to deal with the 3 that look identical today, which are the normal ones when you are trying to find the confidence interval of something that isn't a percentage or a fraction or a proportion, right? Okay. So let me refresh your memory as to what these formulas are. First formula, x bar plus or minus, okay, what is it? Z sigma square root of x. Right? This was formula number 1, the blue formula. The second formula, and you know what, let's see which way is, let me turn this off. Does that make it easier to see or harder? I'm assuming it's making it easier. It took a little bit of the glare away. The second formula is x bar plus or minus z s square root. And the third formula is x bar plus or minus t s square root of l. Okay. In each one of these cases, okay, what we have is we start with x bar. X bar is the average we got from the sample. Remember, the key thing here is that mu is unknown, and what we're trying to find out. The true reality is not known. So what do we have instead? Okay, well, if we don't know what reality is, okay, we're going to have to take a sample and estimate what reality is, right? Mu is not known, okay? What is we have to take a sample. And our sample will have a certain number of observations. If I take a sample of 49 eggs, N is 49. When I take a sample of 100 students on campus, N is 100. Okay. When I am looking at 1,000 random tax returns, N is 1,000. N is the number, okay, in the sample, how big the sample is. Okay, so N is the sample size. X bar is going to be the average from the sample. Right? Okay. So N is the sample size. X bar is the average from the sample. Sigma is the population standard deviation. S is going to be equal to the sample standard. So which of these formulas we use is going to be determined based on two things. First of all, before we get started, what is the same about all of them? Well, what's same about all of them is our estimate, our confidence interval estimate. The middle of our confidence interval is going to be what we got from our sample, right? If I wanted to measure the size of fish in Baffin Bay and I catch 100 random fish, my best guess of what is in the entire bay, right, is the average I got from my 100 fish. Why would I magically change it? It may not be perfect. In fact, I know it's not going to be perfect. I know for certain that it's not perfect. It's an estimate, right? It came from these random fish that I collected, right? But our best estimate is what we got from our sample, this X bar. Best estimate is X bar, right? And then what I'm going to do is I'm going to put a little bit of padding on both sides because I know with certainty that I didn't get it exactly right, right? So what I want to do is put a little bit of padding on both sides so I can make a statement. I am 90% sure it is between these two numbers, or I am 95% sure that the average length of fish is between these two numbers, or I'm 99% or I'm 99.9% sure that the average fish length is between these two numbers, right? For me to be able to say something that I'm 99.9% sure of, right, I'm going to have to put more padding on both sides to protect me from making a mistake. If I'm willing to be okay with saying, you know what, I'm 90% sure it's between these two numbers, yes, I'm implying that 10% of the time I'm going to be wrong and the actual reality is going to be a little bit outside of my interval, right? Okay. If I'm willing to be wrong more frequently, I can give a more precise answer. If I were to be shot, okay, if the answer I gave in my confidence interval turned out to be wrong after the fact, I'd be extremely, extremely careful, right? And I put padding on both sides, a lot of padding on both sides, so I don't make a mistake, right? So if my boss comes to me and says, Schumann, I need you to give me an estimate of what the length of fish are in Baffin Bay, what your guess is to what reality is, right? And he says, oh, by the way, if I find out later on that the interval you gave me didn't include what reality was, and that reality was outside of that, we're going to tar and feather you. Okay. How do I respond to my boss? He says, you know what? I'm going to tell you something that I am 100% sure of. And the boss says, now you're talking. Right? What am I going to do? I'm going to put so much padding on both sides that I know that my statement won't be wrong. I will tell my boss, I took a sample of fish out there, and I can tell you with 100% certainty, I can guarantee on my life that I am not wrong.
that the average length of fish in Baffin Bay is between minus infinity inches long, or 0, because you can't have a fish less than 0. The average fish length is between 0 and 6.5 or 6 trillion miles. That length is between 0 and 6 trillion. At which point my boss will fire me. Why? Because what did I give him? I gave absolutely useless information, right? But was I right? Was I right to make the statement that I'm 100% sure, okay, that the length of fish is between 0 inches and whatever I said, 6 miles, right? Yeah, I know really somewhere in there. Okay. I can say it with 100% certainty. I'm 100% right. I'm sure it's inside. But the boss says, I can't do anything with that. It's like you told me nothing. Yeah, but I told you something I was 100% sure of. Right? I know I'm not wrong. He says, yeah, you're not wrong, but I can't do anything with the information. Tell me something useful. All right. So I was like, okay, I'm going to give you a 10% confidence interval, a 90% confidence interval. I will give you something I am 90% sure of, but you better not tar and feather me, okay, if I'm wrong, because how often will I be wrong? If I'm 90% sure it's between two numbers, how often am I wrong? Well, how often am I going to be right? 90% of the time, right? I have a 90% confidence in that interval I'm going to give you. What is the implied probability that reality is outside that interval? 10%. And my boss says, you know what? You can't give me something. I'm going to go to the press with it. You can't give me an estimated range that is only 90% chance of being successful. Give me something you're 99% sure of. Fine. You want a 99% confidence interval. And the boss says, yes, that's what I want you to do. Give me a 99% confidence interval. Right? The bottom line is the level of confidence is going to depend on your business situation. What are you going to use this information for? If it is mission critical, okay, you probably want to be a little bit more certain. If I am working for NASA and we are trying to figure out, okay, something about shooting a live person to Mars, okay, chances are NASA's not going to be terribly happy with somebody saying, you know what, I'm going to give you a 90% confidence interval. I'm going to accept the fact that 10% of the time what I'm going to tell you isn't true. Okay? NASA's going to say, we can't live with that. If we make our plans based on what you say and you're wrong, this person's not going to Mars. They're going to Venus. Actually, they're probably not going to Venus. They're just going to go out and never see anything again. They're eventually going to run into the sun or some other star and burn up. Can't live with 10% wrong. Can't live with a 90% confidence interval. So, okay, how about a 99% confidence interval? NASA says, can't do that either. 1 out of 100 times? No. All right, how about a 99.99% confidence interval? That means 1 out of 10,000 times I might be wrong. That's it. Okay, we can deal with that. Our astronauts know there's a risk, and that is such a small risk that you're going to be wrong. Why don't we do a 99.9%? 99.99% confidence, right? It depends on the business situation, okay? If you are sending someone to the moon, you need a higher level of confidence than if you are trying to get some information because you're going to put it into a brochure for visitors as to what a great fishing location Claybrook County is, right? You write something in your Claybrook County, Kingsville brochure trying to get visitors, and you come up with an estimate of how big the fish are, and it turns out that the fish are actually just a little bit bigger than you said, just a little bit smaller than what you said. First of all, the visitors probably aren't going to know, and they're not going to be terribly upset either, right? It's not going to change the outcourse of history, right? And so Claybrook County, if you were trying to get information because they want to put it in a marketing brochure for the area, probably are more willing to have a smaller confidence level than NASA would be. Right? It depends upon the business situation. Right? But either way, the middle is going to be from what we got. Right? This is what we got from the survey. The X bar is the survey mean, the sample mean. Right? And then what's behind the plus and the minus are how much we put padding we put on the up side and how much of that padding we put on the bottom side. Okay? I like to talk about this as being the level of padding, right? Because I think we all understand that. Your book uses a more scientific measure, and that measure is the margin of error. The margin of error is how much we are putting on both sides. Right? I like to think of that just plain as how much padding are you putting on the higher side? How much padding are you putting on the lower side? Okay, but the technical term is the margin of error. Okay. I wouldn't use margin of error because chances are people you're talking to probably haven't taken a stats class in a while. They don't understand the word padding. Okay, right? And the key thing is, as somebody doing stats for business, you're trying to communicate to the folks what's going on. Okay. Well, what's the difference between 1 and 2? Well, in Formula 1, we knew what sigma was. Sigma is a Greek letter, right? It is the true value of how much variation there is in the population. So for some reason, God or some God-ish entity told you what sigma was. Even though, why couldn't that person just tell me what mu was? Come on, right? Okay. If God or your professor or something, or your boss says, by the way, we know what sigma is, we use this formula. If we don't know what sigma is, we use one of these two formulas. And in this formula, we replace the sigma with an S. And then we just go on with life as if nothing happened. Okay. We just say, you know what? We don't know what sigma is. S is the sample standard deviation. I'm just going to plug the sample standard deviation in instead of the population standard deviation because we don't know what that is. And hopefully we're not going to be too wrong. We're going to be wrong a little bit, right? Because this isn't reality. Just like X bar isn't reality. What we computed from the sample isn't reality either. It is just what we saw when we looked at, the 100 fish that we took from the bay. Right? We will have come up with an estimate of how much variation there is in fish in general, right? But it's not a perfect estimate. What we basically say here in Formula 2 is, we're going to use S anyways, right? Now, if we knew what sigma was, we would use sigma because that's what God tells us reality is. Don't use S. Now, we use this formula when we feel confident that our S is not far away or not statistically significantly far away for our purposes. And what does it mean? Well, it means our sample is big enough. The smaller our sample, the worse our estimate is going to be. Both this and that, by the way, right? Okay. But the smaller our sample, the less confidence we have that our S is really a good approximation for sigma. So what do? We use S because that's all we got. And we use this formula because N is large. What does N being large mean? It is greater than or equal to 30. It turns out large isn't that large. If you've got a sample over 30, just replace sigma with S, and you're relatively good to go. If N is less than 30, then what we have to say is, you know what? Replacing sigma with S gives us a little bit too much uncertainty. And because we have too much uncertainty, we don't feel comfortable about using the same formula as we did before because we are likely to be wrong a little bit more. Why are we likely to be wrong? Well, we're likely to be wrong just for the same purposes we always were likely to be wrong. But since our S is going to be possibly wrong, then that formula doesn't work anymore, the one that we did up here. So what we end up doing is we end up saying we cannot use a normal distribution anymore. We need to use what is called the T distribution. The T distribution. So the only thing different between this one and this formula is this Z and this T. Right? What did we have here? That Z was the Z level that corresponded with our confidence level. I'm just going to call confidence level of alpha. If alpha equals 0.95, the Z on the table that's in the back of the book, the Z value that has the area between minus Z and positive Z on the standard normal, okay, is 1.96, minus 1.96. Don't believe me? Go look it up in your books as well, right? Minus 1.96 will tell you that this area here is 0.0250. Okay. Your book will tell you from minus infinity to here, including this area here, which we're going to erase, but from here all the way to here is 0.9. Oh, look that up on the table. What is this area that we care about? 0.9750 minus this blue thing. Subtract. Minus 0.0250. 0.005. So the Z value that corresponds to 95% is inside here. If we wanted alpha to be 90%, okay, we're going to have a different Z here. And by the way, we're going to end up with a different T as well. Now, to find this, if this in the middle is 90% instead of 95%, how much is in each tail? This is 5%, or 0.05 is in this tail, and 0.05 is in that tail, right? What Z value has 0.500? To find this, we need to go look at a T table, right? And so let me get down to my computer and find a T table, a Z table to show you, not a T table, a Z table to show you, okay? So we're gonna look for the Z that corresponds to 90%. Okay. So search Z table. Okay, I have one on your share application screen. Okay, I have, I think, a Z and a T table on our main content page, home page. And you guys should be seeing the home page right now, is that correct? Normal table, page 1. All right. You guys see, somebody can just verbally say, yes, we see it. The cumulative normal probability table.
Yes, we see it.
You see it. Okay, thank you very much. Because when I show something like here, I can't see what you guys see. And I've been known to talk about things for an hour. All right, so what we are looking for is what? When we look over here, this is the shaded area. If we're looking for the Z value that has 90% in the middle, we are looking for the Z value that has 5% in the left-hand tail, right? And there's going to be 5% on the right-hand tail right over here as well. But we can, in our table in the back of the book, okay, we are going to look inside of here for where we have 0.0500. 0.0500, because the inside of the normal table gives us this area, right? And on the top and on the sides, actually starting on the sides, okay,
It gives us our Z numbers, but the area is in the inside. And when you guys did your assignments early on, what you did was you found the Z value, and then you found the probability inside of here. What we are going to be doing now is doing this backwards. We are looking for 0.0500. 0.0019, 0.017. Here we're at 0.11, we're too high. 0.0548, that's close to 0.0500. Well, if I go here, that's, whoops, a little closer. Even closer. Even closer. 0.0505. Wow, that is really close to 0.0500, right? Well, if I go over one more, it's 0.4950. Where is 0.0500? It's halfway in between these two numbers, right? What is the Z value corresponding to this number? Well, that number is minus 1.6. What's minus 1.6? And then I'm going to go straight up to get the last digit. That first number is minus 1.64. The next number here, the number we're looking for is right where my pointer is, right? Halfway between those two numbers. Okay, do you guys see my pointer? I don't know whether you guys see it. Okay. Well, it's halfway between 0.0505 and 0.495. This number here was minus 1.64. This number is minus 1.65. So what's halfway between 1.64 and 1.65? It's 1.645. Okay. So now you guys are seeing me again, hopefully. Is that correct? You guys see me? Share camera.
Yes.
Okay. All right. So if we had a confidence level of alpha equals 90%, this Z value would be a minus 1.645. On the other side, it would be a positive 1.645. And the Z value up here is 1.645. Okay. So we did a 90% confidence interval. This Z number or this Z number would be 1.645. If we were doing a 95% confidence interval, that was 1.96. Sorry about the phone. Okay. Hopefully my brother will call again. Okay. So if we had a different confidence level, an 80% confidence level, we'd have a different Z that corresponds to it. So the Z number you get from reading the Z table in the back of the book, but you're reading it backwards, right? The T number we are going to get from the T distribution, right? And that one is in the back of the book too. And it turns out that this one is going to be actually an easier table to read. right? So what I am going to do is pull that up, share application screen. And do you guys see a T-table, a stats table right now?
Yes.
Okay, good. That's great. Slideshow. Maybe this is a little bit bigger. Okay. This table, okay, I'm going to make this view bigger. View, zoom. This table is in your back of your book. I think I grabbed this one off the internet, so it's not a, I think this one has a little bit more detail on it than the one in the back of the book. But in the back of the book, it is the T distribution, okay, is on page 570, okay? And if you look at the diagram, it shows you what it is that the table shows you. In this particular case, it is highlighting the shading the right-hand side instead of the left-hand side, okay? Which is what the other tables do, right? Which is why you should always only use tables which show you a diagram of what the numbers are showing you, because different textbooks will show you different things and they won't always be consistent, right? And what you have here is you read this one backwards. This one is going to give you the shaded area that you're interested in, right? In the case of 90% confidence intervals, we said we wanted 5% in each one of the tails, right? So the top row, we find the column that has the heading 0.05. Right? So the T value that has 5% on the tail, which corresponds to a 90% confidence interval, right? If 90% is in the middle, how much is in each one of the tails? Well, 90% in the middle says 10% is in both tails, which means 5% is in one tail, right? So if I look down this column, okay, and it will turn out, okay, that I need another number. I know that the T value is in this column, but I will need the degrees of freedom. Okay. The degrees of freedom, okay, is n minus 1. Remember, n is how big the sample was, right? If your sample consisted of 10 fish, 10 minus 1 would be 9. Which column were we in? We were in this column here, which would give us our T value of 1.833. So in this case, the middle of our table is the T value, and the top is the probability, the shaded area. Remember, that is completely the opposite direction of the normal table, right? But in order to use the T table, we need to have an understanding of how good our estimate is of S. And the larger our N is, the larger, the better our confidence is. The more confidence we have that S isn't far off,
the smaller our padding is going to need to be. So the smaller our t value is going to be. And if I just look down this column and I go all the way down to the bottom, you'll notice that this column gets very, very close. We get to 30. And by the way, this particular table after 30 gives up. Why? Because we said if you have an n larger than 30, just plug in the z value, right? The neat little thing is in the very, very last column of the z table, the t table, it will give you the z value as well. So you can easily cheat to find the z value by looking in the wrong table. It is a lot easier to find the z value for a confidence interval by looking at the last line in the t table. In this particular one that I pulled off the internet, it is labeled as z, just in others, like the one in your book, it is labeled as infinity. If you have an infinite number of observations, you know what reality is so well, right? An infinite number of observations will give you essentially the value of the normal curve, which is 1.6448. Rounding like I did before, 1.65. Right? Okay. So this is how we use our t-table to find the values. Okay. So we do this, we go to this table when we are in this situation. Okay. And let me go back so I can see what you guys are seeing. So when I point to the board, I can see that I'm pointing to what you guys are seeing. Right? So here, if we have a small n, we know we're going to have to go to the t table to figure out what the t is that has the amount in the tails that correspond to our alpha level, our confidence level, right? And if we look at the very, which row do we look at? Well, we go down to the n-1. It's called the degrees of freedom, and it is n-1. Why is it n-1? Because remember when we talked about taking a sample? And I said a sample of one person or one item, right? Gives us a little bit of information as to where the middle is, right? What the mean might be. It's not a very good estimate, but it's the best we got, and it gives us some information, right? It doesn't give us any information about the variance or the deviation that exists in the population, because the first observation we have about how different items are comes from the second observation. That first observation is useless. And so when we do the degrees of freedom, we take our n, let's say n is 100. We have 100 observations, but that very first observation gave us zero information about how much variation there is. And after that gave us some additional information. Right? The degrees of freedom are the observations that give us information. So it's n-1. Why don't you just write n-1 in the table? Well, I don't know. I think they should. Right? Well, there's technical reasons a little later on that you will have a degree of freedom. Okay, but n-1 is for what we're going to be doing primarily. If we wanted to get the Z, just go to the T table, go to the wrong table, and then go all the way down to the bottom, because we can just read off the Z value that we're looking for. Okay. If we go to the actual table that we want to see, you got to read that one backwards. And you're probably going to have to extrapolate and so on and so forth. The T table is the way to cheat to get those data. Now, it won't give you all of the percentages. Okay, the T table is out there for the ones that are most common, right? 5% in the tail, 2.5% in the tail, 1% in the tail, 0.1% in the tail. Those, there's a column for. You want an 87% confidence interval? I'm sorry. The T table won't have that for you. Now, you could go to the library and get a big fat CRC table where the Z table is not one page, but 80 pages long and a lot more detail. And they'll have all the rows. So if you wanted an 87% confidence interval, you could find it. But that's not a norm. Normally, people ask for round numbers like a 90% confidence, 95%, 99%. The ones that are almost always common, those are the ones that show up on the T table. All right. I am going to call it quits right now. And then what I'm going to end up doing is I'm going to put a couple homework problems out there for you to attempt, right? And I'll put a due date next week on those. And then on Monday, we will do a couple examples and get you comfortable. And then on Wednesday, we probably will go and add at least two more, maybe three more formulas for very specific situations. All right, and that would be in the things that we will do next week would be branching out into chapter 8. I think we're in chapter 7 now, if you guys are keeping up with the textbooks. All right, are there any questions? No questions? All right, well, in that case, have a great weekend, and we will see everybody on Monday. All right? Okay, bye-bye.